Now, of course, let us first look into some of the properties that I'll slowly look into every algorithm and then say how does this algorithm do? Is it very good? Is it very bad? So bet first search operates like this in a bet first manner. Let us, for the bet first search, discuss in some important properties. The first property that I call is completeness. An algorithm is called as complete if the algorithm guarantees to give you a solution provided one exists. So can the BFS solve the problem of going from India to USA in the modern times? There's no connectivity. No, there's no such path. You cannot take a flight. You cannot go walking. You cannot swim. The army or the navy of both countries will stop you. So we look at when a solution exists. So if a solution exists, does the algorithm guarantee to give you the correct solution? And let us see whether BFS will be complete or not. Now, we've already assumed that a solution exists, and let this be the solution. And because a solution exists, it will be at some depth d. So let d be the depth at which the solution exists. Now, at time 0, I am guaranteed that I have got the source. That's the first step of every bet first search. Take out the source. Yay, you got the source. After some time, I would have extracted in the same order all the children of the source. That's exactly how I go in bet first search. I go level after level. So after some finite time, all the children of source would have been explored for sure. After some more time, all the grandchildren of source would have been explored for sure. After some more time, all the great-grandchildren would be explored. So after some time, I have visited all nodes at depth 1, then after some time all nodes at depth 2, then after some time all nodes at depth 3, and after some time, because I visited all the nodes possible at a depth d, therefore, I would have definitely visited the goal. You cannot mix that. It's at depth d. You visit all the nodes at depth d, you have visited the goal at depth d, and therefore you have found a path at depth d. So, yes, BFS is complete as long as your edges, which is here, or your branching factor, which is here, is finite. In all AI problems, the branching factor, this needs to be finite. The second property that we'll discuss is more interesting. It's called as, is the algorithm optimal? Optimality is the property of the algorithm to give the best solution only and nothing but the best solution, adhering to the constraints and the assumptions taken in the problem already. So let's find out if BFS is complete. And now let me take not one goal. Let me take, this is one goal which is possible. That's another goal which is possible. That's the third goal which is possible. That's the fourth goal which is possible. There are two ways you can think about multiple goals. In some problems, they are actually multiple goals. So it's raining, I want to go at shelter. Any place where it's not raining is a shelter. Hundreds of places like that. The second, tree search, every node will get injected multiple times. If a node comes 5 times in your search, you don't stop that. I've only visited that. Tree search, and remember by default, my assumption will be all searches are tree implementation, unless I've otherwise mentioned. So, because of that, I'm readmitting node. That means even if the goal is found multiple times, it will get readmitted. Now, this is at a height of d. Let us say this one is at a height of d plus 2. This is at a height of d plus 5. I need to ensure the lowest cost, which is this is the goal which gets discovered and not each one of either of these three. Now, it's assumed that goal exists. Of course, otherwise there's no need to even solve it. We assume that there is a solution to the problem. And the best cost that it exists is D. It does not exist anywhere less than D. It may exist in more than D. Now suppose I am at a depth of, let us say, X. So I extract out the node, I look at its depth, it's X. I look at its cost, it's X. That means because I go level by level, that means the nodes which are at the depth of X are currently being explored. I look at this node and it is at a goal. So let us say a surprising thing happened during search. So I discovered for the first time a node that satisfied the goal criterion. There may be many goals at a depth which is also the same as cost X. Now I need to prove that X is equal to D. Otherwise optimality doesn't hold good. And we'll do it intuitively. Of course, we won't do it formally. Now X cannot be less than D because there exists no goal at a cost less than D. So X can definitely not be less than D. If X is equal to this D plus 2 or D plus 5, then there's a contradiction because before processing D plus 5, before processing D plus 2, I would have visited all the nodes at the depth of D, and after visiting all the nodes of depth at the depth D, I would have got the goal, and because I would have got the goal, that means this cannot be the first time. So because I go level by level, because I go layer by layer, that means the first time I look at the goal, the first time I extract the goal, at the depth X, it has to be D. It cannot be D plus 1, D plus 2, D plus 3. Of course, it cannot be less than D. Otherwise, I won't get the goal. And therefore, I say that yes, the BFS is optimal. And of course, the standard criterion that for graphs which have all costs as the same, or all the step costs are 1, only in that case the BFS is optimal. So the more interesting property, which of course is to deal with complexity. I'll deal with two types of complexity here, the memory complexity as well as the time complexity. So let us do the time complexity first, and let's calculate how much of efforts have we spent in around over here. So again, I'm going level by level and I am stopping when I look at the goal. Let's just do the classic old way. Let's count the total number of nodes. and the total number of nodes will be how much of effort I have experienced. So this parent has B children. This parent has B children. Why B? What's the maximum number of actions that I can apply? Up, down, right, left. It's B, the branching factor. And that's exactly why I said it will be called as a branching factor, because now it denotes the number of branches. One parent gives rise to B children. B parents give rise to B square children. One parent gives rise to B children. B parents give rise to B cube children. And finally, let's say I was so unlucky when I was processing depth D, goal was the last node. Had there been one more node, it would have gone in depth D plus 1. The luckiest, when I process depth D, the first node to be found is the goal. Sum this up. So it's a geometric progression 1 plus B square. If you process that B raised to D minus 1, the complexity of course comes out to be B raised to power D, which is the complexity of breadth first search. So the time complexity for both tree search and a graph search, remember, in that, I did not say whether it's a tree search or a graph search, whether I'll prune revisited states or I won't. In both cases, it becomes B to the power of D. And the memory complexity is I need to store the entire tree, so it's B raised to power D. It's funny, you only have a frontier, but because those frontier have parent links and those parents have parents link, the entire tree is stored. So the memory complexity is B to the power D, which is also the time complexity. Ever in AI, somebody asks you what's the complexity of BFS, do not answer this. Because in AI, this is infinity. Okay, it's not literally infinity in most cases, but this number is so large that we assume it's infinity. It's not practically possible. You may have a move for 8 puzzle problem in 3 or 4 moves, 9 factorial, very big number. And E is, of course, B times V, the maximum. So if V is infinity, this is also infinity. Why quote the complexity as infinite? Don't do that. On the other hand, 8 queens problem, B is how much? 4. D, how much deep solutions will I give you if you need to play as a child? 5 moves, 6 moves, 10 moves? So maximum you need to move 20 times. So this is 5, 6, 20, 25. So 9 factorial. Now, unluckily for this problem, still 9 factorial is not that large a number as it appears. However, there could be cases where the state space is absolutely infinite and B raised to power D will be reasonably finite. So never report your answer as V plus E. In fact, the joke in AI is that how do you solve the problem when you cannot store your graph itself as either an adjacency list or an adjacency matrix? You cannot. Can you do it for a game of chess? No. Could you do it for going around as a nice body where you have 25 degrees of freedom? That means the state with all the angles are 25, each one of them discretized by 10, by 1 degree each, could go 360. So the state space size is 360 raised to power the number of degrees of freedom, which is 25. No, you cannot even store it as an adjacency graph. It's impossible. So when you cannot even store it as an adjacency graph, as an adjacency list or an adjacency matrix, you still need to do a program. That is what makes AI programming a little bit different from how you do it as BFS in terms of the second semester and the fourth semester data structures and algorithms. So never have any program, never have any complexity, never have anything in terms of total number of vertices and total number of edges, because believe me, it is practically infinite. And because it is infinite, you'll never be able to get to this very large graph. You won't be able to store it with the 2 GB, 3 GB, 10 GB, 25 GB, whatever is your RAM size. You just won't be able to store it at the first place. You can never enumerate the entire graph for sure. You can never have a loop for I is equal to 0, I less than number of vertices, I plus plus. The number of vertices will not even fit your memory. So, never report anything in terms of number of vertices as well as the number of edges. Now, I'll quickly take in the other one, which is obviously Dijkstra's algorithm, and in AI for reasons we call it as the uniform cost search. The reason why we do that is, of course, Dijkstra's algorithm, line number 1, put all the vertices into the priority queue. Excuse me, there are infinite vertices. Is the first step gonna be infinite time taking, infinite memory taking, infeasible? No. So it's a uniform cost search. Let's take in the same example very quickly, that I need to go from CC1 all the way to an ATM. So let's say this is CC1. I won't do the complete example, of course. And let's say these are just vertices B, C, D, E, F, and that's my ATM. Luckily in this case, even if you do a Dijkstra's algorithm, the number of vertices are low finite, it's a well-defined graph. So all you'd say is that you start over with CC1, the edge costs are like this, 5, 3, 4, 13, 12, 8, 7, 6, 2. At the cost of 0, then you could go to A, you could go to B with a cost of 3 or 13. So this becomes 3, this becomes 13, and so on and so forth. I won't do that for sure. And the name is go to A, and this is go to B. And similarly, you can have the tree search equivalent of it or the graph search equivalent of it. Now, uniform cost search is just because my priority queue will grow like the BFS. It'll start over with empty and I'll just keep on adding elements up over here. The rest of the complete processing is exactly same as Dijkstra's, and therefore I can completely avoid speaking anything about this algorithm. Similarly, the breadth first goes depth by depth. The uniform cost search goes cost by cost. So in breadth first search, first everything till a depth of 0. In uniform cost search, everything till a depth cost of 0. Breadth first search, then everything till a depth of 1. Uniform cost search, then everything will a depth of, in this example, 3. So first everything which has a cost of 0, then everything which has a cost till 3, then everything which has a cost till whatever comes up over here. You go around this, cost controls, cost by cost. And therefore, you know that with the same ideology, I should be able to define in all the same things around over here. So that's my uniform cost search. Yes, it's complete because you assume that the solution exists at a cost of C star. You go cost by cost, 0, then some epsilon, then some 2 epsilon, then some 5 epsilon, 0, 5, 10, 12, 13, as per the specific algorithm. And because this cost contours keep on increasing, somewhere you will extract all nodes with a cost of C star, then you'll get the goal. So it's both complete and optimal. And the complexity also will, of course, be exactly the same. The caveat here, of course, is that the cost cannot be negative. Of course, in AI, the cost cannot be negative. Now, unfortunately, I cannot say b raised to power d. And therefore, let us quickly say, how did I get b raised to power d? So, it was all the way up over here, 1 plus b squared plus b cubed, all the way up to b raised to power d. So rather than drawing this thing, let me draw a much simpler thing. So let this be the path from source all the way up to the goal. So we know that this has a cost of C star. It's continuous. I've drawn a path, by the way. You imagine this entire tree going around with till a depth which I don't know. So the complexity is, of course, b raised to power d. The problem is I do not know what is this d. So let's calculate what is this d in terms of what I know, which is C star. C star, by the way, is the cost of the optimal solution. So I can write down b raised to power total cost divided by the cost of each step. That will give me d, the total cost divided by the cost of each step. Now, after reaching a solution of C star, your search stops. And therefore, let's say I need to maximize this term. What's the maximum cost node that I ever visited, C star? What was the least cost step node that I took? It's epsilon. So epsilon here is the least step cost that you get en route. It's the least step cost that you get en route. It could be extremely small for problems, like you could get two intersections very close to each other. So, but then epsilon can be calculated. Now, you cannot have b raised to power something which is a float. D has to be integer. So let me bound this to an integer, and it becomes b raised to power, using mathematical tricks that you know, 1 plus floor of C star by epsilon. So it's still b raised to power d, except for d was unknown. The d was unknown, as in d is the length of the longest path that I have ever seen till I get the goal. D was length of the longest path that I've ever seen. The depth of the goal was, of course, known, but the depth of the longest path that I've ever seen till I reach the goal was unknown. So I say that, okay, I derive what will be the length of the longest path that I've seen, and the derivation turned out to say that the longest path that I've seen is 1 plus C star by epsilon, and that's exactly what is the complexity. Please note, C star is the cost of the optimal solution. After C star, I stop, so I don't care about what happens after C star. C star is the optimal cost. Epsilon is the minimum step cost or the minimum edge cost, which could be very small, extremely small. And that's why you see that the complexities usually turn out to be much higher. Again, please do not say V plus E. Saying V plus E is linear, yours is exponential. Excuse me, not. V could be infinite. In AI, the graph is not always a finite graph. So, and yes, V itself has exponential to the number of state variables. V is the state space size. That is exponential on the number of state variables. The degrees of freedom raised to power the resolution per degree of freedom, if you want to be exact. Of course, I give more senior people these definitions. So that is what is a uniform cost search.